From playing soccer to building moon bases, robots that can go almost anywhere. I'm Tonya Hall for ZDNet and Tech Republic, and joining me is Dr. Marco Hutter. He is the co-founder of Anybotics and assistant professor for Robotic Systems at ETH Zurich. Welcome, Marco. Give us a brief summary of your resume and what prompted you to start Anybotics. What problem were you trying to solve?
So we started about 10 years ago to work on walking machines, so machines that have legs that can go to arbitrary environments. And then for the beginning, we were for a very long time just figuring out methods for how we drive them, how we can just walk with them. And then realized about after 5-6 years that there's a really, really big need for these types of machine out in the wild for different types of applications. And that's what essentially triggered the foundation of a spin-off company that is now really working towards commercial application with these machines, and also continues the work that we are doing here, both at the robotics lab and also at the company.
You've concentrated your robot development efforts on 3 areas: interaction, autonomy, and mobility. From that, 3 products have emerged. Let's start with AnyDrive.
So the AnyDrive is a compliant actuation module and essentially evolved from the development of series elastic actuators for our walking machines. Series elasticity is very helpful for different reasons. First of all, the compliance that we integrate in our system helps us in protecting our machines. So if we get impulsive loads from outside, we don't break the gearbox. We just absorb these shocks in the spring. The second is that we can use this spring in order to store energy. That makes us much more powerful and much more efficient. So very similar to what we see also in the muscle tendon systems of humans and animals. And a third one is that by having a spring, we essentially can measure the spring deflection, which gives us a very nice sense of what kind of torque that we're applying in the joint. And we can use this then in order to regulate really the dynamics of our machine. And this we first developed in small prototype units that we had on our walking machines, and then turned into really compact modular unit that are driving now all kinds of different machines, from walking robots over arms, exoskeletons, to very simple, basic robots.
Explain the technology behind AnyBalance.
AnyBalance, in essence, is the core technology behind how to make a system interact with its environment in order to optimally balance for stability and this interaction force distribution. So that essentially also evolved from the development of walking robots. A walking robot has multiple legs that are in ground contact. And typically, especially if you're standing on uneven ground, you have to optimally distribute this ground reaction force. And it turns out that there's many machines out there that have very, very similar problems. So we did a technology transfer from small scale, 30 kilogram heavy walking robots to really huge excavators, 12-ton heavy, that are going to very crazy environments. But so far, these were all position-controlled machines, so they had to permanently, actively adapt the suspension in order to move across challenging grounds. And now with our technology, that really optimally adapts the ground reaction forces among all these different contact points. This is a very smooth process. The operator doesn't have to do anything with that. It's just a machine that stays in the environment as it's supposed to be.
You brought these 2 technologies together in Animal. So what else does she do besides play soccer?
These days, Animal is primarily used for industrial inspection. So we were just 2 weeks ago, we were on an offshore site in the North Sea, where this robot for the very first time was doing a fully autonomous for very long duration inspection of these facilities. So imagine you have a mobile platform that has the potential to go to any place a human can go. You put all kinds of sensors on it. These are regular cameras, these are thermal cameras. You can have also acoustic sensors, all kinds of different sensors that allow you to really perceive, observe, and survey your environment. And you process this data on the machine itself in order to figure out how much pressure you have somewhere, if a boiler is overheating, if a geometry has changed in the environment. So all these type of things that today, you have to fly out humans to check that the things are running well, and then you have to fly them back, which is very expensive, can be extremely dangerous, and it's probably not the job that most people would like to do.
What are some of the specifications for Animal? I mean, how much can it carry? How long does the battery last? I mean, how steep can it climb? Those types of things.
So the current version of our robot is about 30 kilograms heavy. So we wanted to build a machine that can be essentially carried along by one single person. So not too heavy, but at the same time not too small, in order to make it capable of overcoming obstacles that we have in our daily environment. So if you look at an infrastructure, typically it has like steps, it maybe has stairs, some gaps, some small obstacles. And that's where we can like really go without any like crazy maneuvers, like climbing maneuvers that we have to do. And we wanted to have a machine that can do locomote in the same environment. So that means the robot has, with its leg length, about 0.5 meter. It can overcome obstacles, which is really close to the leg length. So at least like 30 centimeters of height. We can run with about 1.5 meters per second top speed, which is about like human walking speed. And battery lifetime at the moment is roughly 3 hours. And of course, it really depends on how much payload you want to give to the battery. So here we're talking about like 3 kilograms of battery for 3 hours of lifetime. Now, what is cool is that the machine features a charging station where the robot can essentially just come back to the charging station, sit down, plug itself into the power, and recharge. So we get essentially in an autonomous mission scenario, you get like a permanent operation time.
How many Animal robots have you built so far?
So there were a number of prototypes we developed for our own research purposes. Now, from the current series, there is about 6 out there already in different groups and for different applications. And we are building about the same number just right now. Hopefully, this is increasing in the short-term future.
How do users program the robot for specific tasks based on, what you're trying to accomplish?
So we are providing very different level inputs for the users. Most of the people, like me as a researcher, I want to really program that to the lowest level details. So essentially, we give them the complete software framework that we have developed. People can plug in their specific code they want. It can be from a small state estimator to a high-level navigation algorithm to like something that just does a new visual inspection of your environment. So you have really the freedom to plug in your modules as you want. Most of the software is also ROS-based on a high level, at least. So even if people are not very familiar with locomotion control, they don't want to bother about an algorithm to figure out what is my proper foothold in order to move. They can just take the algorithms that exist and plug in a high-level intelligence or control or navigation algorithm as they want.
Were there any surprises or significant technical hurdles to overcome in the development?
Of course, this is why we do the research in this area, and that's why it's so interesting. So in my eyes, legged machines really belong to the most complex machines you can think of. The reason for that is primary two. The first one is you have to coordinate a huge number of degrees of freedom in order to make the systems move. So in our robots, it's about 12 actuators that we have integrated. Think about a car. A car, essentially, what you have to control is speed and turning, but that's more or less it. For these walking machines, you have to coordinate much more degrees of freedom. The second big challenge is that you're continuously interacting with the environment at different locations and at different times, and that makes it so tricky. So if you compare this to a drone essentially just has to fly around. Of course, it has to balance, but it has to fly around and just not make contact with anything in your environment, and you're going to be safe. Now, for a walking robot, this is very different. You have to make permanently contact with the environment at locations you might don't know exactly what type of dynamics is there, what can I expect from this ground reaction at that moment in time, and that makes it so tricky in order to move around.
What's next, Marco?
I hope and actually strongly believe that we're going to see such walking machines in all kinds of different applications. So as I said before, right now, from a commercial side, we are primarily tackling industrial inspection. but there's much more. So I have research projects right now that are deploying such machines in the sewers. So last week we're here in the sewers of Zurich. There's hundreds of kilometers of underground tunnels where you have humans, you have maybe very, very primitive machines that move around and try to inspect this. We want to have machines like Animal that can take over these jobs, that you don't have to send humans to these working places. The same project is actually a European cooperation that we have with different partners. Also tackles the application in a copper mine, where we have the robot inspecting conveyor belts to make sure that there is no fires anymore underground, 1,000 kilometers underground, which is can have really dramatic outcome. We are now working on like very future application, which is for space. Think about how we're gonna go to Mars or Moon and build a landing station or a habitat up there. This won't be humans going up with a shovel and building these houses. You're gonna have robots that can go there, explore interesting places and build stuff. And for this, we need to have much more capable locomotion concept as today. So we won't be able to just drive around because traditionally there's no streets up there. So legs are probably one of the most promising applications. And then of course there's other things like entertainment, education, and all kinds of potential applications which are right now not in the primary focus, but can certainly, by someone who's interested in taking Animal to do something crazy, go for it.
Dr. Marco Hutter, co-founder Anybotics and assistant professor for robotic systems at ETH Zurich, making walking robots to protect humans from places they maybe shouldn't go. Thanks so much for taking some time to join us and shed some light on this topic. If somebody is interested in connecting with you, maybe they're interested in learning about walking robots, how can they do that?
Well, you can check out our YouTube channel, like Robotics. You can check out our homepages, both at ETH, rsl.ethz.ch, or Anybotics, so www.anybotics.com.
Thanks again. And if you guys want to find more of my interviews, you can do that right here on ZDNet or Tech Republic, or go to my website, tonyahall.net. I've got links to all my social sites. Thanks for watching.